All right, guys, we got kind of another doozy a little bit because we're, getting toward the end of the book. So this one, I'm going to leave out a little bit of the stuff maybe that your book does, or actually other books. I'm not going to prove everything for you. I really want to get to showing you examples for this. So the idea here is that we're going to do a change of variables now, just like we did in like Calc 1 and at the end of Calc 1, at the beginning of Calc 2, when we talked about doing substitution. When we do a substitution, like let's say we're going from, why is that orange? Let's say we have an integral 0 to 2 of 4 times 1 plus 4x dx, and this thing is to the 1/2. Okay, so we will make a substitution, right? We'll let u equal 1 plus 4x, right? And then we see here du is 4 dx. So we have a really nice, substitution here because I wanted it to be. And then we looked at when x is 0, right? U would be 1, and when x is 2, it looks like u is 9. So then we go from 1 to 9. So the idea here is we want to start thinking about that as a transformation of regions, okay? And mainly, I'm not going to worry about the integrand so much, but really what I'm going to worry about more is what is the region that I'm going to be, well, in this one we'll kind of look at both, but what I'm going to care about more in when I'm dealing with double integrals is I'm going to care about more is how do I change the region, right? The bounds on my integrand, or on the integrals, the R that I'm going to be integrating over. Just like when you had to do the change, you had to change the order of integration. You had to look at the region you were integrating over and then think about how we're going to slice up that region in different ways. Same thing here. So if we look at what happened here, when I was in terms of x and y, right? Here was x, here was y. What was I integrating over? So in this case, it's not a region, right? Because we're just have a single integral, but this was what I was integrating over, right? 0 to 2. And I was integrating this function. When I put in 0, what do we get? 4, right? Yeah, because it's 4 times that. I'm 0 here at 1/4, and this guy kind of looks, well, I'm going to exaggerate it a bit. It's a square root function, but because of the, because of the 2, 3, 4, the 4 out front, it kind of grows pretty fast. Like when I put in the 2, I'm at 12. So the area under the curve that I'm finding then is going to be this area, right, in terms of x and y. So when we do a substitution, really what we're doing is a transformation. So we're taking we had x and y, and now instead of x and y, I would have u as my x-axis, and then maybe, I don't know, let's define v to be like my y. So now I'm integrating v equals the square root of u, and now I'm going to be integrating this from 1 to 9. So this green space, this that I was integrating over now is changing to 1 to 9, right? And now I have this function where these areas, the green and the pink, are exactly the same, right? They would give me the same number, but I've just transformed it. So we're going to call these transformations, where they're called linear transformations. You may have heard of them if you've had, we haven't talked about in linear algebra yet, but you may have talked about them in differential equations. But we're going to think about this as a linear transformation T, okay? Now, what's going to be difficult is I put my arrow going from xy to uv, but technically it goes both ways. And the way we're actually going to think about this is that when I let u equal 1 plus 4x, I could solve this and I could say x equals what? 1/4 of u minus 1. So I could think of it as a transformation this way also. So this would be u and this would be v. Okay, we've done this. I mean, we did this with substitution. We've actually already done it in multiple integrals. We just didn't really think of it that way in multiple integrals. So polar coordinates are a transformation, right? So like if I had, for an example, 0 to 2, 0 to the square root of 4 minus x squared, e to the x squared plus y squared, let's say dy dx, I could change that. Then we get 0 to pi over 2, 0 to 2, because this is a circle, right, with radius 2, and I just want the first quadrant, e to the r squared r dr d theta. So this is going to look a little bit different, right, because I'm dealing with an entirely different axis. So what this says is that if this is r and this is theta, r is going to be between 0 and 2, right, and then theta is going to be between 0 and pi over 2. So here's pi over 2. So this is actually the area that you're integrating over, right? What did we know it looked like over here? Technically, if it was x and y over here, right, we knew it was a semicircle. So what happens is that semicircle, even though we don't see the green square normally, has actually been we've transformed this, right, with this t. And we can say that our theta and r can spit out our x, or we could put in x and y and spit out r and theta. So depending on what I solve the equation for, it's a relationship between x and y and r and theta. Okay, I hope that kind of makes sense. Okay, so let's start talking about this and write down a couple of things, and then I want to do some examples. So change of variables in a double integral. So why would we do this? Just like we would do in a single integral when maybe we have an integrand that is difficult to take the antiderivative of, it is easier sometimes to change it. And now we have two variables to change, right, instead of one. So what we're going to do here is we're going to find a transformation. That transformation is going to involve two equations. Okay, so we're going to find a transformation that relates u and v to x and y. We just choose u and v because of u substitution, right? So something similar. So basically what we have is we have xy then is some transformation of my u and v. Okay, now normally we say u equals some function of x, but it doesn't matter, I could solve that either way, right? Where x is going to be a function of u and v, and y is going to be a function of u and v also. Realizing that actually in practice when I do this, this is kind of mathy. That's a new word. I should say I'm kind of mathy. This is a little mathy. What we're really going to do is we're really going to have like u equals a function of x and y. That's pretty much how we're going to see it. But we need to look at both ways to be able to do the transformation, okay? So what basically happens is no, I don't want it to be a circle. I want it to be a bean. This transformation, right, I have a point uv. This transformation takes that uv and then puts this relationship to our r that we're used to from before, right, into some point, who knows where that point is, but into r. Okay, so we define r to be the transformation of s, and this is what we call the image of s under t. Okay, so I want to write, we have like two more things to define, and then I just want to go and start doing examples. So I'm going to skip the example number 1. You're welcome to look at that in your in the book. But example number 1 is kind of like what I was talking about up here in a really fast way, but I'd rather do these in examples with taking antiderivatives and stuff. Also, when we talk about a transformation that's one-to-one, what that means is that when we talk about this transformation being one-to-one, then if I have t of something equals t of q, then this implies that p equals q. That's basically like when we're in R2 passing the horizontal line test, right? So what this says is that I have an inverse transformation. That means I can go both ways. This is what we call a linear transformation is one-to-one. Not linear transformation, but this is a one-to-one transformation. I'm not going to write down that definition because we have enough to do in this section, but I want you to realize that that is true. Okay, so here is our goal. Our goal, okay, is to take some integral r f of xy dA, and we want to transform it using t into something that is more simple. So now I have this s, and I know that looks, so we're really going this way, right? We have s where we have f of x of some u and v now, y of some u and v, and then I still have a dA. Now, this is where we're going to get into a little bit of trouble as this dA, because I don't necessarily have that nice pretty rectangle anymore, right? I might not have that at dx dy. So this dA right here, we have to use something called a Jacobian. So let's write that down. It reminds me of like the Jabberwocky. Why does it remind me of the Jabberwocky when I say Jacobian? That scared me back in the day. You guys remember that? Look up the Jabberwocky in the Alice in Wonderland. Alice in Wonderland was actually quite scary. So given a transformation t, so here's my transformation. X is going to be some function of u and v, okay, and y is going to be some function of u and v, where of course like g and h have to be nice, right? Where g and h are differentiable on the uv plane. Okay, then the Jacobian, we call it, not the Jabberwocky. This is named after a mathematician who kind of worked on looking at how to transform things to different axes. Okay, so this is the Jacobian of t, of this transformation, is given by this. So j of uv is going to be the partial, we'll say, of xy over the partial of uv. And what this ends up being, okay, is it's going to be the partial of x over the partial of u times the partial of y over the partial of v minus the partial of x over the partial of v times the partial of y over the partial of u. So it actually reminds me a little bit of like the sum and difference formulas in trig. Because we just like switched them. So notice I take the partial of x with respect to u times the partial of y with respect to v, and then I subtract those two switched, okay? And where this is gonna go is we're gonna put that in that dA right there. It's kind of like the factor that we have to account for to take maybe a rectangle, which like we did up here, right? We took a rectangle and it was we took a semicircle and transform it into a rectangle or vice versa. But this Jacobian is going to be kind of the price we have to pay for that, okay? Now, one way you could memorize this is if you think of this as the determinant of, this is one way to remember it, but you guys will have your notes, right? But it does kind of help to do this. So if you take the determinant of this y of this matrix, this is just, it doesn't actually have anything to do with linear algebra, you guys. It's just a way to remember how to get this. So remember, determinant of a 2 by 2, you multiply these two together, which gives you that, right? And then you subtract the product of those two, which is that right there. So remember, that's how you find a determinant. And so what do? You take the partials of x on the top here, right, with respect to u and v, and then on the bottom is the partials of y with respect to u and v in the respective order. So this is what we call the Jacobian. This is what, and once we do it, some examples, it'll be so much easier for you to see what's going on, hopefully. Hopefully I don't mess that up too much. But once I do a couple examples, you'll kind of see where that Jacobian comes in. Again, it's kind of the price we have to pay. It's the factor of taking something in xy and moving it, that region, in uv. All right, so let's write down this theorem, and then we will be ready to do, I think I have 3 examples for you, and then for sure work on the fun sheet for this one too. All right, so here's our theorem. You might want to pause it, write it down, and then start it again. Okay, welcome back. Okay, so here's our theorem. We have t is a transformation where x is equal to a function of u and v. We'll call that g of uv, and h is the function, h of uv. It maps s in the u, so s is in the uv plane onto r in the xy plane. Okay, but we really want to kind of think of it the other way, right? Assume t is 1 to 1, meaning that 1 point, like if uv goes to some xy, that's the only one that goes to that one, right? If 2, 3 is mapped to 4, 7, we don't have another one mapped to 4, 7, okay? All right, on the interior of S, and that g and h have continuous first partial derivatives. I need that because of the Jacobian. then if f is continuous on R, we can make this transformation. So a couple things here. So this dA right here, depending on what we're going to do, this is going to be du dv, or it's going to be dv du, okay, one of those. And then another way to kind of think about this Jacobian maybe is, you know how we had to have, like, when we did the you know, when we did U substitution and we had to have the derivative of the inside kind of sitting there, that's another way to kind of think of that Jacobian, why I have that there. It's kind of to pay the price for the partial derivatives and stuff that we're going to be dealing with. All right, you guys, we just got to jump into this and we got to do some examples because that's the only way we're going to really understand that. Really quick though, now we're just going to go into terms of examples. It's interesting, if you look at example 2, you should look at example 2 in your book on page 1075. What's cool about this example is it shows you that the Jacobian for polar coordinates, right? If you look at the Jacobian for polar coordinates, you see that it's R. And remember, dx dy, right, or excuse me, dA completely in polar coordinates is r d theta. And so it's pretty cool that you can see that the Jacobian, when you're dealing with that transformation, is R, which is what we should expect it to be, because this is just, again, it's just a change of variables in multiple integrals. Okay, so let's do one. So sometimes you will be given what the transformation is going to be, and then sometimes you have to decide what it's going to be. So I'll give you an example of one where they tell you what they want you to use for your transformation. So we're going to have this example right here. So I'm going to be integrating x minus 1/2 y. Because I have y as my bounds, that must mean I'm going dx dy. So we're going to evaluate that by using the substitution. So what do we want x to be? We're going to set x equal to u plus v and y equal to 2v. Now this is really, this one is going to seem kind of random. Why? Well, you were given that substitution. Now, the next two we're going to do, you're going to see where we'll kind of pick the substitution ourselves, and maybe it'll make a little bit more sense as to why we picked that substitution. But for right now, they're going to tell us that this is the substitution that they want you to use. Okay, so here's what we have to do. So I know that this x right here is going to be replaced with u plus v. Okay, that's not going to be too hard to see, right? So for my integrand, it's not going to be that big of a deal. And then this y right here, I'm going to replace with 2v. So for the integrand itself, I don't have a whole lot of work to do. Now, what work do I have to do? I have to figure out the Jacobian, right? So I'm going to have to figure out the Jacobian of u and v. And I have to figure out how I'm going to change these bounds right here, because those bounds right now are in the xy plane, and we want to see what is that corresponding region in the uv plane. Okay, it's going to be okay, I promise. So let's look at what R is. So remember, this is my region R over here, and let's look at kind of like what is R going to look like. Okay, so let's see what R is bounded by. So the easiest probably is to look at the dy. dy is bounded by 0 and 4. Okay, so I know that my y values are going to be bounded by, right, this is y equals 4, and this is y equals, no, that's not. This is y equals 4, and this is y equals 0, right? All right, there we go. I can do this. It's going to be fine. Okay, let's see what happens with, so let's look at what happens here. So when y is 4, right, 1/2 of y, that would be 2. So that means that x is 2 when y is 4. So I know then that I'm at this point right here, and I know that that's going to be a line, right? And when y is 0, x is 0. So this is a line. Okay, and then when y is 4 with this one up here, I would have 2 plus 1, right, which is 3. I don't, sorry guys. Oh, 3 in the x direction. I was just really confusing myself. So when y is 4, x is 3. Because remember, this is equal to x, right? Oh my gosh. And then when y is 0, x is 1. Okay, so I have kind of, oh, I don't like that. I have this like, oh, that wasn't too bad, Sarah. Pretend like there. Oh, look at that. Good job, Microsoft Whiteboard. For once. That should be like perfect there. But this is the region that I'm integrating over. And now I have to figure out how these two, right, substitutions are going to switch me into u and v. Okay, so I want to see how I'm going to be switched into S, okay, where I have this is U and this is V. And I don't know if it's going to be in the first quadrant. Well, I do know it's going to be in the first quadrant because I've already done this, but I'm not sure what it's going to be in. But I need to figure out, I need to kind of sketch that so I can figure out what my bounds are. So when you have something like this where you have the lines, the easiest way to do this is actually just to look at, now you can't do this if you don't have straight lines. If you have curves, it's going to be a little bit different, but because they're straight lines, let's look at all of the points and see what happens to each point. So I have the point 0, 0, I have the point 1, 0, I have the point 3, 4, right? And I have the point 1, 4. So I want to see what is going to happen to these points under the transformation that I've been given. Oh, 2, 4, I'm sorry, that's a 2. 2, 4, and 3, 4. Okay, so again, what is the relationship? I know that x is equal to u plus v. I know that y is equal to what? 2v, right? So when x is 0, so we got to do a little bit of work here. So what I'm going to do is just solve these really quick for v and u. So v is going to be 1/2 y. The reason I'm solving is because then I can just plug these points right back in, right? And I don't have to really do much work. I don't have to solve like a system of equations every time. And so what would u equal? Well, what do I have? U is going to be x minus v, but what is v? It's 1/2 y. Okay, so this is my transformation. These are all the equations that are going to relate my x and my y's and my u's and my v's together. So when x and y are 0, notice that u is also 0, right? And v is 0. So I'm going to get the point 0, 0. So this green point right here is going to just transform to 0, 0 right there. What about when I have x is 1 and y is 0? So if x is 1, right, then up here and y is 0, that shows me that u is 1. In v, when x is 1 and y is 0, v is just 0. So I'm going to have the point. So this point right here is going to transform to 1, 0 right here. So that's kind of interesting. Those 2 points in the denominator on the bottom didn't transform at all. Okay, so when x is 2 and y is 4, I would get, right, when x is 2 and y is 4, I would get 2 minus 1/2 times 4. So I get 2 minus 2, so u is 0. And then what about my v? Well, half of 4 is 2. So I'd be at 0, 2. Okay. So then this point right here, this point 2, 4 is transformed to the point 0, 2. Okay, so I'm right there. And then finally 3, 4, if I plug that into my formula, I would have 3 minus 1/2 of 4. So 3 minus 2 is 1. And then I would have what? V is 1/2 y, so that would be 2. I'd go to 1, 2. And so this point right here is going to be transformed to that point. So look at what our new area is, right? It's going to be, u is going to be go from 0 to 1, and v is going to go from 0 to 2. Okay, so that's what this transformation has done. Is that this is my new area that I'm integrating over. Just like at the very beginning of this, sorry, I don't want to make you sick. Apparently I do want to make you sick. This green, right, was transformed into this pink. These are the new it's the new region that I'm integrating over. That's exactly the same here. Okay. All right, guys, so here we go. So the integral, oh, we also needed the Jacobian. Okay, so remember, x we know is u plus v, right? And y is 2v. So the Jacobian of uv, I'm going to take the determinant of, okay, take the partial of x with respect to u is 1. Partial of x with respect to v is 1. That's my top row. Partial of y with respect to u is 0. Partial of y with respect to v is 2. And then remember, I multiply these two and I subtract the product of those two. So my Jacobian is 2. Okay, so that's basically kind of the factor that I need to multiply by to make sure that everything's gonna work out okay. All right, here we go. So my original integral, right, was this one, 0 to 4 of x minus 1/2 y dx dy. Okay, so what is this going to transform to? I'm going to have the integral of, now what is x equal to? We found what x was equal to, right? Well, we know x is u plus v. So this x right here is just going to become u plus v minus 1/2 of, what was y? Y was 2v. So that'll be pretty easy. Right? So that's my integrand. And then my Jacobian is 2, absolute value of 2, which is just 2. And now I have to decide, do I want to integrate with respect to u or v first? Actually doesn't really matter in this case. I think if I see, kind of look at what's going to happen here, I think we'll integrate with respect to u first and then v. Now, where is u bounded by? Notice u goes from 0 to 1, and then v goes from 0 to 2. So this is going to go 0 to 1, 0 to 2. Okay, I know that this didn't seem easier. It's probably not. If I were to integrate that original double integral I gave, I would not probably do a change of variables, but we're doing this because it's fun. Remember what you're feeling right now. Oh, I need parentheses. It's fun. So look at this. Half of 2v is just v, so I get v minus v. So I just have a u left over. So basically I have 2u du dv. So that is 0 to 2. That's u squared from 0 to 1 dv. Okay. Yeah, right. Yeah? Yeah, okay. And if I put in 1, I get 1. If I put in 0, I get 0. So I get just 1 dv. So that'll be just v evaluated from 0 to 2, which is 2. Oh, all that work for 2. All right, let's do another one. This is going to be fine. It's going to be fine. You're going to like it. I'm here. I'm here to help. You might want to ask me questions about this stuff. So let's evaluate this integral. Let me get rid of some of this. Okay, so let's evaluate this integral r, and e is going to be raised to the y minus x over x plus y dA, where r is the region in the first quadrant quadrant with vertices. Vertices? Is it how you spell vertices? Sure. 1, 0, 0, 1, 0, 2, and 2, 0. Okay. All right, so I'm not giving you a substitution here. So we got to figure that stuff out on our own. Okay. So let's see what my R, well, first of all, what kind of substitution am I going to be making? This one, I think hopefully it's pretty obvious that, I think I'll let u equal the top of my, the top of my fraction and v be the bottom of my fraction. That usually works out pretty well if you can see something like that. So let's just let u equal y minus x and v equal x plus y. Okay, I think that'll probably be the easiest. So let's go ahead and solve for x and y, because again, that's going to be one of the easier ways. Well, actually, I don't even really need to solve for x and y. Nah, well, let's see. We might need it. We might not need it. But I'm going to let u equal y minus x, and I'm going to let v equal x plus y. Well, yeah, I have to solve for x and y because for my Jacobian. So let's wait for that for just a minute and let's see kind of what happens. Let's first talk about what my r and my s look like. So r, here's what I know. I am bounded by, right, 1, 0. Whoa, let's try and make that a little bit better. 1, 0, right here, 0, 1, 0, 2, and 2, 0. So my R then is going to be this region right here, okay? So I got to think about this region. I have 4 sides to this region, and so what are the functions that I'm going to be bounded by? Well, this function right here is just y equals 0. That's pretty easy to see. And this function right here is just going to be x equals 0, right? Okay, now I also could, we probably could just take the vertices and kind of see what happens. That actually might be a little easier. Let's do that right now. Let's take the vertices and see kind of what happened, and then we'll figure out something for x and y. I was going to go and like find the line and everything, but I don't need to do that because I know they're all bounded by lines. So again, this is 1, 0, 2, 0, 0, 2, and 0, 1. So let's see what we're going to get for s under this u equals y minus x and v equals x plus y. So let's see what happens. And because I know what's going to happen, I'm going to give myself a little bit more room. Let's let this be u, let's let this be v, and I'm going to need 2. Okay, so let's look at the point 1, 0, right? If I plug 1, 0 into y minus x, I get 0 minus 1. So u is going to be a negative 1. And if I put 1, 0 into x plus y, right, that's going to be just 1. So this 1, 0 is going to transform to, whoops, negative 1, 1. Okay, what about my 2, 0? My u would become 0 minus 2, which is a negative 2. My v would be just those two together, so I'd have negative 2, 2. Okay, so there are my points there. Now, what about 0, 1? That would be 1 minus 0, which is 1, and then 1 plus 0, which is 1. So I'm going to have 1, 1. And then finally 0, 2, right? I'm going to have 2 minus 0, which is just 2, and then add them together, I get 2, 2. Okay, so here's what S is going to look like, and then I'm just going to connect the dots. La, 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 la. Whoa. So this is pretty great. So look at what my, oh, that's lovely Microsoft Whiteboard. Good job. So there's my new region, and this is going to be pretty awesome. I got to think about how I'm going to slice this up, right? I don't think I want to slice it up this way because notice I would have, you know, a different bound on here and here when I'm trying to figure out my dA. Do I want to integrate with respect to u first or v first? But we'll probably take this sucker and slice it up this way when we do that. And so what I need to figure out is I need to figure out what am I going to be bounded by, right? So if I look at the equation of this line here, so this point right here is 2, 2. Let's use a different color here. This point is 2, 2. This point is 1, 1, right? So it looks like I have slope 1. If I extended this line, it would go through the origin. So through the origin with slope 1 would be y equals x. But remember, I don't have y equals x because it's u and v. So really what I think about is, okay, u is basically my x and v is my y. So this line right here is basically v equals u. Okay, and then this line right here, and if you're not sure how to do that, you could just take the slope between those two lines and then put it into slope intercept form or point slope form, and then just do that all on x and y's and then replace your x's with u's and your y's with v. Likewise, this line right here is the same thing, right? It's going to go through the origin but has a negative slope. So this is going to be v equals negative u. Yeah. The top one obviously is just u equals 2, and the bottom one here is u equals, not u, excuse me, v. Because it's a horizontal line, right? V. All right, I think we're almost ready to go. The last thing we have to do is find the Jacobian. So when we find the Jacobian, we do need to figure out U and V Jacobian. We do need to find x and y in terms of u and v. So look at what I have here. I have u equals a negative x plus y, right? And I have v equals x plus y. If I add these two together, notice, what would I get? I would get u plus v equals 2y. So that tells me right away that y is equal to 1/2 of u plus v, okay? Now to find x, I'm just going to plug this in for my y here, and I'm going to solve for x. So that says that x plus 1/2 u plus 1/2 v, I'm going to just go ahead and put that 1/2 through, equals v. And now let's just solve for x. So what does x equal? This is going to equal, if I take away a half, I get 1/2 v minus 1/2 u. Okay. So those are my equations. So I know that, again, x equals 1/2 v minus 1/2 u. And I know that y equals 1/2 u plus 1/2 v. I'm going to multiply that through because I know I need, that's a v. They're partial derivatives, and I think that'll be easier just by kind of looking at it. So my Jacobian, right? Partial of x with respect to u is a negative 1/2. Partial of x with respect to v is a positive 1/2. Okay, partial of y with respect to u is 1/2. Partial of y with respect to v is 1/2. So then I'm going to multiply these. So that's a negative 1/4. Then I'm going to subtract minus 1/4. So it looks like my Jacobian is a negative 1/2. Oh, I don't know about you, but this is exhausting. The good news is I can only really put like one of these on the test, right? How would I put two of them on the test? Okay, guys, so I know my Jacobian is a negative 1/2. Okay, so let's come back over here and let's look at what we have. So we're going to have, remember our initial integral, right, was e to the, what was it? Y minus x all over x plus y dA. And this was all over r. So now we're going to switch this to b over s. And I'm going to have e to the, what am I going to have? U over v, right? Times the absolute value of a negative 1/2. That's my Jacobian right there. And now we decided we're going to have to integrate, I'm sorry, with respect to u first, right? I'm going to have to do, I think I maybe said v. du dv. So what is u bounded by? Well, down here, if I solve this, u equals a negative v. So it's bounded on the bottom by a negative v. It's bounded on the top by v, right? And then where can I take, what's v bounded from? 1, 2, 2. Okay. I hope that makes sense. Okay, guys, this is going to be okay, I promise. Now we're integrating with respect to u, so we're going to treat v like it's a constant, right? So I'm going to bring that posit, that 1/2 out. I'm going to integrate from 1 to 2. That v, this v down here is just going to be a constant. So how do I take the antiderivative of e raised to the ub? Well, if I took the antiderivative of e to the, let's say, x over 2, right? The antiderivative of that would be 2e to the x over 2. Does that make sense? Because I would divide by that 1/2. So here I'm going to get v e to the u over v evaluated from negative v to v and then dv. And remember, I'm going to put that in for u. So I go 1 to 2. If I put v in for u, I get v e to the first power, right? Because v divided by v is 1. And then minus v e to the negative 1 dv. Okay, so I strongly recommend factoring out a v, and I'd be left with e minus e to the negative 1. That's just going to be a constant from 1 to 2 v dv, right? And then we get 1/2 e minus e to the negative 1. And then I have, what, 1/2 v squared from 1 to 2. So that will be, let's see, 2 squared is 4. Divided by 2 is 2. So 2 minus 1/2, which is 3/2. So basically, what do I get then? Basically get 3/4 times e minus e to the negative 1. Whew. What do you think? Yeah, Not too bad. I hope it's not too bad. What are we at? We're at 40 minutes. Yeah, let's just kind of see really quick what's going to happen with one more of these, okay? And then maybe I'll let you, finish it out. But I want to show you one more just how to set this up. So for my example, let's evaluate the integral over r of y squared dA, okay, where, let's talk about what r is. Where r is the region in the first quadrant bounded by, here's what we got, x equals y squared, x equals y squared minus 4, x equals 9 minus y squared, and x equals 16 minus y squared. Okay. All right. So, let's see what's going to happen here. Who knows? So I need to draw this out first, and let's see if we can figure out what sort of substitution. Now, I know I'm in the first quadrant, right? Here's what else I know. I know that these are just parabolas. So y equals x squared is just going to be a parabola like this, right? This is, x equals y squared. And then the graph of y squared minus 4 is going to be something, let's see, when y is 2, right, we're going to be at 0. And so we're going to have something like this. This is x equals y squared minus 4. And then when we look at it the other way, 9 minus y squared, that negative just flips that parabola and makes it go this way, and then it shifts it to the right 9. So I'm going to have, this is not going to be perfect. I'm not going to worry about it being too perfect here, but this is going to be x equals 9 minus y squared. And then the 16 is going to be the same. Do something like that, right? So I should have switched those a little bit. But this is the area. This r right here is going to be this area right here. Okay, and we're going to see, we got to make some sort of substitution to figure out what we want to happen there. So the way we're going to kind of look at this is I'm going to consider my two parabolas kind of pointing to the right and my two parabolas pointing to the left, because I could actually, if I look at this, right, and I subtract that y squared from both sides, notice that I could have x minus y squared equals negative 4, and then I would have x minus y squared equals 0. So look, if I let u equal x minus y squared, do you see how that's really nice? Because what does that show? That just shows, what is u going to be bounded between? It's just going to be bounded between 0 and negative 4. Isn't that kind of crazy? I like that. Yeah. Likewise, if I kind of consider my parabolas facing the other way, which was the 9 minus y squared and the 16 minus y squared, if I add the y squared to each side, I have x plus y squared, right, equals 9. And then x plus y squared equals 16. So what if we use this? We made the substitution v equals x plus y squared. So this is my r. If I make those substitutions, if I let u equal x minus y squared and v equal x squared plus y squared, look at what this says. It says that v is going to be between 9 and 16. So if I look at my s then, right, u, remember, is my x-axis. Okay, so what is my new area going to be? I'm going to go from u is negative 4, right, negative 4 to 0. Okay, and then v is going to go from 9 to 16, wherever that is. So I'm going to have then this new area right here. So that's pretty cool. That was actually pretty nice. That's pretty amazing. Look at what we've taken. It's going to be much, well, maybe not much easier, but it's going to be easier because we're going from something where our bounds were going to be kind of nuts, right? If we think about the bounds on that double integral to something where my bounds are just going to be constant. So that's pretty great. Okay, we still have to find the Jacobian. So remember, we're letting u equal x squared, nope, just x minus y squared, and v is equal to x plus y squared. So to find the Jacobian, I have to figure out what x equals and what y equals, right? So if I just add these two together, notice if I do u plus v, then the y squareds cancel out and I just get 2x. That's pretty great. So right away I know that x is equal to 1/2 u plus 1/2 v. That's funny that we get that again. Okay, and then what is y going to be? Well, y, right, is going to be v minus x, right, which that would be y squared would be that. So I'd have v minus 1/2 u minus 1/2 v, because I'm going to subtract all of that x. So that looks, if I combine like terms, that's 1/2 v minus 1/2 u. But remember, please, that we have to square root that. Ew! And I'm going to take the positive because I'm in the first quadrant. So this is the square root of 1/2 u minus 1/2 of v. So this is a lot. I'm going to just really quick tell you what the Jacobian is. We're at 46 minutes. So I think I'll kind of get this set up and then I'll let you look at what to do from here. But the Jacobian, if you look at this, I'm going to have 1/2 and 1/2. Now the partials with respect to y aren't as quite as easy because we have to use the chain rule. I'm going to have 1/2 u minus 1/2 v to the 1/2, right? So I'll just go ahead and if I take the partial of that with respect to u, I'll tell you right now we get a negative 1 over 2 times the square root of 2 times u minus v. Okay, and then here I'm going to just get a positive 1 over 2 times the square root of 2 times u minus v. I don't know if you're still with me. I feel like you're not. I don't know. So if I multiply those together and then add the multiple of those together, you actually just get 1 over 2 times the square root of 2 times, oh, v minus u, I'm sorry. V minus u. That should be v minus u. V minus u. V minus u. Okay, so that whole thing, which I know it seems like this maybe wasn't easier, but I think it might be. If I integrate, I'm going to go -4 to 0, so that says I'm integrating with respect to u first, then 9 to 16, right? Well, y squared was pretty easy to see. That was just 1/2 of v minus u, right, before I had to square root it. Then the absolute value of the Jacobian, I don't have to worry about an absolute value because I'm dealing with square roots. 2 times v minus u du dv. The 2's, oh no, the 2's don't cancel, but you can simplify that. It's actually not too bad to do. You would rewrite this as this, right, times v minus u to the negative 1/2, sorry, 1 over that, right, and then take that guy and put it out front, and then it actually isn't too bad because notice these are the same, so it's not too bad to take the antiderivative of. I'm gonna go. I'm worried that you left a long time ago, so now I'm just talking to an empty room. I don't know, or a person banging their head on the wall. I hope that's not true. Hey, you gotta reach out to me. Please don't wait until Monday to start on this homework. Plus, get ready for the test next week. So I know we're kind of in crunch time here. Let me know if you have any questions.